In this little video, we're going to look at the equations of motion. We're not going to worry about where they come from, we're just going to look at how they're used to solve some simple problems in physics. So first of all, let's just have a quick reminder of them. There they are there, or at least those are the most important ones, the most commonly used ones. You may see some of them in slightly different versions. Sometimes these equations are very straightforward to apply, but when we're thinking about vertical motion, and in particular where we've got vertical and horizontal motion together, then it can be a bit more complicated, and there are several things we have to remember. Firstly, all of the quantities we're dealing with, displacement, velocity and acceleration, are vectors. So they have direction. The direction is important, and that means that sometimes we might have to use a positive or a negative to indicate the direction concerned. Secondly, horizontal and vertical motion are completely independent of each other. That means we have to treat them both separately. Sometimes this is a bit difficult to remember, difficult even to believe, but it is very important. Finally, sometimes there's hidden information, and what I mean by that is perhaps there's information that's not explicitly stated in the question, but that you need to use to solve the question. For example, if an object is thrown upwards, we know that when it reaches its maximum height, its vertical speed, its vertical component at that point is 0. It's no longer moving upwards, it hasn't started to come back down yet. Its vertical velocity is 0. That won't be stated in the question, so it's an example of one of those things that you have to remember. Now let's have a look at how we might apply these equations to some simple situations, and we'll start with probably what is the simplest of all, an object being dropped. So we're going to drop an object from a certain height above the ground. Let's say that height is 40 meters. And what we're normally asked to do is to calculate the time taken for this object to reach the ground. So let's think first of all about what we've actually got here. We know that the vertical displacement is 40 meters. The object is going to have to fall 40 meters to reach the ground. At first sight, it looks as though that's all we've got. But of course, we do also know what the acceleration is. The object is falling under the effects of gravity, and therefore the acceleration is 9.81 meters per second squared. We also know what the initial speed is, because when an object is dropped or falls, the initial vertical speed is always 0. That's one of those hidden pieces of information I mentioned previously. It's the time that we're trying to find, so now we have enough to be able to use this equation, s equals ut plus half at squared, to calculate the time. This is a quadratic equation in t, and that can look a little bit scary sometimes, but almost always one of the pieces of the equation will be 0 and will disappear. And in this case, of course, it's the u. U is 0, so that part is going to disappear, which makes it a lot easier to solve. So we have our 40 meters as s, and we know that equals half 9.81 times t squared. All we have to do now is rearrange it to solve it. So that will give me t squared equals 2 times 40. That gives me 8.15. So t, of course, is the square root of that, which is 2.86, or let's keep it just to 2.9 seconds. You might have noticed there that despite the fact that the acceleration due to gravity is downwards, we didn't use a negative with the 9.81. It's not always necessary to do that, and in this particular question we've got nothing acting upwards. We've got no upwards velocity, no upwards acceleration, and no upwards movement at all. So it's not necessary to make that distinction. We could, if we wanted, put a negative before the 9.81 to denote that it's downwards. But in that case, we would also, for consistency, have to give a negative before the 40, because the displacement is also downwards. And so the two negatives, one on either side, simply cancel each other out and make no difference at all to the final calculation. Now let's look at an example where we do have some upwards motion. So let's think about what happens where we have an object thrown upwards. Now let's say in this case that we're going to throw our object upwards at 12 meters per second. And we might be asked to calculate, for example, the maximum height this object reaches before it falls again. And we might be asked to calculate the time it takes to return to the ground. So we're going to try both of these. Starting with the maximum height, and let's think again about what information we've actually got here. We know that our initial speed is 12 meters per second. We know that the acceleration is 9.81, and this time the negative is important because we have to show that it's in the opposite direction from that initial speed. Oops, that's a 2. We know that at the maximum height, the speed of the object, the vertical speed, the vertical velocity is 0. So that's the extra bit of information there that we need to enable us to find that vertical displacement. Thinking back to the equations of motion, the one that best fits the quantities we've got here is this one. V squared equals u squared plus 2as. So we've put our numbers in. V was 0. U was 12. Don't forget the minus here. 2 times 9.81 times s. When we rearrange this though, this part here, when we move it to the other side, it's going to lose its negative sign. So let's just do that now. 2 9.81s are 19.62. And 12 squared is 144. So that gives us a displacement of 144 over 19.62, which is 7.3 meters for our maximum height. The other thing we have to do here is to find the time it takes for the object to come back down to the ground. Now we're going to use some of the same information here. We know that the object is thrown upwards with an initial speed of 12 meters per second. So our initial speed hasn't changed. Our acceleration, we know, is 9.81 with a negative because it's downwards. We're trying to find a time, and we're going to need one more piece of information to be able to do this. Now, if you think about what's happening to this object, it's being thrown upwards and it's coming back down after it reaches its certain height. When it reaches the ground again, it's back down to where it started. Its vertical displacement is 0. It's at the same point vertically where it started, and that's the extra piece of information we need. So we're going to take our vertical displacement as 0 and use that to solve this question. So looking at what we've got there, the s equals ut plus half at squared equation is the most appropriate one. And this time, looking at it, it's the s that's 0, so it's this piece that's going to cancel out. So let's put in our numbers. We know 0, 12t plus half, remember the minus there. When we rearrange it again, this other piece is going to lose its negative when we take it to the other side. So this is what we have. Now, we have a t on one side and a t squared on the other. So if we divide both sides by t, we lose one of the t's on the left-hand side and we lose the only t on the right-hand side. So we've now got something a little bit simpler and we can work this out. So half of 9.81 is 4.905 or 4.91 if you want to continue with just 2 decimal places. 4.905t equals 12. So all we have to do now is rearrange this. And we end up with 2.4 seconds. 2.4 seconds for the ball to return to the ground.